This is the review for the test on solutions. We're going to start with the solubility graph, and the first four questions refer to this graph in different ways. So question 1, how many grams of sodium chloride can be dissolved in 100 grams of water at 50 degrees Celsius? So the amount of water, 100 grams, okay, the chart is based on 100 grams of water, so we don't have to do anything with that. The temperature in this case is 50 degrees, so we're going to be on this line at the 50. And we're looking at sodium chloride, which is this line here. Okay, so we're going to look for the point where the 50 meets that line, and then if we follow that back across over to here, it's slightly below 40. So we're going to say at 50 degrees in 100 grams of water, we could dissolve roughly 38 grams of NaCl. Okay, that's a give or take, that's a guess. For this one, if you had come up with anything between 35 and 40, that would have been fine. On the test, I'll try to make sure that they're less vague than that and that they're pretty spot on in terms of the numbers. But that's how you work the chart. You find the temperature you're looking for, where that intersects the line of the substance that you're looking at, and that tells you how many grams you could have at that temperature. How many grams of ammonium chloride will precipitate if a saturated solution with 100 grams of water at 90 Celsius is cooled to 50 Celsius? So again, the 100 grams of water is already taken care of. We're looking at going from 90 down to 50. So we're moving in this direction from 90 to 50, and we're looking, this time we're looking at the line for ammonium chloride, which is this line here, and at 90 degrees Celsius, we're right about here on the chart. So that's roughly 70 degrees. And then when we drop the temperature down to 50, we're at this mark, right, because we follow that line up. We intersect there, and we go from 70 to 50, because we're moving from 90 down to 50 Celsius. So if you started with 70 grams and the solution can only hold 50 grams at the lower temperature, then the amount that will precipitate out is the amount that it can't hold anymore. And the difference between 70 and 50 is obviously 20 grams. So that's how much will precipitate out if you lower the temperature from 90 to 50 degrees, following that line from the 90 point down to the 50 point, from 70 grams down to 50 grams. How many grams of potassium nitrate will dissolve in 300 grams of water at 20 Celsius? Okay, so now we have to look at the grams of water, because in the chart we have 100 grams. In the question, we have 300 grams. The way we're going to figure this out is, well, at the temperature, which is 20 degrees Celsius, at the temperature we're given, how much would we be able to dissolve in 100 grams? And then if we had 300 grams of water, we could dissolve 3 times that much, right? Because 300 is 3 times 100. So we're looking at potassium nitrate, which is this line here. And at 20 degrees, if we go up, we would have, let's say, it's right up just above the 30 here. If we zoom in a little, we could even call that, let's call it 35 just to make it a round or even number. So we could have 30 grams in 100 grams of water, 35 grams in 100 grams of water. That's what the chart shows us. It's based on 100 grams. So if you wanted to set it up as a proportion, you could say, all right, if I had 300 grams, how much potassium nitrate could I do? Well, that works out to 300 times 35, and then divided by 100, which works out to 35 times 3. So the number of grams I could have would be 105. 35 times 3 grams. So that's the answer to that one. So how many grams of water will it take to dissolve 400 grams of sodium nitrate at 40 Celsius? So this one is working a little bit differently. So we're given an amount of sodium nitrate. So here is sodium nitrate way up here. Okay, this is the line we're looking at. And the question is at 40 Celsius, so that's this line. Well, if we look along that line, the line for sodium nitrate hits that line right about 100 grams. Right? It says we could dissolve 100 grams of sodium nitrate in 100 grams of water at 40 Celsius. So then it's really about 1 gram to 1, right? It's 100 to 100. So therefore, if I wanted to dissolve 400 grams of sodium nitrate, I would need 400 grams of water to do it. And that's the answer to that one. So 4 times as much as could be dissolved in 100 grams of water means I'd need 4 times as much water, 400 grams of water. Decreasing the pressure of a liquid solution will do what to the solubility of gases? So gases, when they're dissolved in liquid, for example, like in a soda, they become less soluble. Okay, gases are less soluble in conditions of low pressure or high temperature. Okay, low pressure or high temperature make gases less soluble. Again, if you think of the example of the soda, low pressure, when you open the can, it releases the pressure, and that's when the bubbles can come out. Also, if the soda is warm as opposed to cold, it goes flat, loses its bubbles, loses the gas much more quickly, because gases are less soluble when you raise the temperature. So the question here was, if I lower the pressure or decrease the pressure, that will decrease the solubility of gas solutes. It would also be decreased if I raise the temperature. For example, increasing the temperature of a solution will decrease the solubility of gases in a solution. Okay, so if you decrease the temperature or increase the pressure, that would increase the solubility of gases. But in both these cases, we're doing things that decrease the solubility of the gas. There was a bit of a typo here. This should say salt. Okay, why are salt and water? Well, they're soluble. We know that salt dissolves in water. Okay, so that rules out these two answers. Because salt is predominantly ionic, and water is very polar. So in fact, none of these answers really fit. But so the saying again is like dissolves like, which means polar and ionic substances will dissolve in polar solvents like water. Water is very polar. Salt is very ionic. Other polar substances dissolve very well in water. Nonpolar solutes dissolve in nonpolar solvents. So oils do not dissolve in water because oils are nonpolar and water is polar. So opposites don't attract in this case. Opposites don't dissolve together very well. Adding a solute to a solvent will do what to its boiling point, freezing point, or vapor pressure? Well, adding solute, has the following effects. It increases the boiling point, it decreases the freezing point, and it decreases the vapor pressure. Okay, so these are not correct. Adding a solute will lower the freezing point of a solvent, therefore a solution. Okay, if 1 mole of each of these solutes is added to a certain amount of water, which will have the lowest boiling point, which means which will have the least effect, because adding solute increases the boiling temperature. So which of these would have the lowest or least effect? And what you have to remember here is that anytime you've got something like this, metal, non-metal, A, C, and D, and a lot of times these are things like sodium chloride, magnesium chloride, calcium, or copper chloride. A lot of them have chloride at the end, but it doesn't have to be chloride. These are all ionic. Ionic compounds dissociate or break apart when they dissolve, which means they basically multiply their effect. So CuCl2, when we're doing the formula for boiling point, has an I value of 3 because it's a copper and 2 chlorines. That's what's produced when you break that up. Sugar, or any compound with carbon, has an I value of 1. Okay, so anything that's sugar or has carbon, or anything that says a non-electrolyte, that means it's not going to break apart, which means the I value is 1. So this has an I value of 3. The second one has an I value of 1. Magnesium chloride has an I value of 3 because it's a magnesium and 2 chlorines. Sodium chloride has an I value of 2. So what we're looking for here is the lowest boiling point, or the least effect. The least effect is the one with the smallest I value, which is the sugar, so B. C6H12O6 glucose is a blank and will form blank. Okay, anything with carbon is a non-electrolyte, which means it only forms one particle in solution. So again, sugars, any other organic compounds, if it says organic, if it says a sugar, if it has carbon in the formula, or if it says non-electrolyte, that means it has one particle per mole, or one particle per molecule. How many liters of 3.5 molar solution can be made from 92 grams of phosphoric acid, H3PO4? Well, remember the formula for molarity is molarity equals moles per liter. Well, what I've got in the equation is, the question is how many liters, and I'm given the molarity. So I'm given the 3.25 molar. I'm looking for the number of liters, so that's my unknown, my x. So what I need is the moles, but I don't have the moles. What I do have, though, is I have grams, and the number of moles equals the number of grams divided by the molar mass. So I need to calculate the molar mass of the phosphoric acid. It's a hydrogen plus a phosphorus plus an oxygen, or sorry, 4 oxygens. So the mass of the hydrogens would be 3, phosphorus is 31, and then 4 times oxygen, 4 times 16 is 64. If I add that together, I get 96. So if I divide 92 by 96, the number of moles is 0.958 moles. So now I have moles. I can plug that back into my equation over here. 0.958 divided by the number of liters gives me the 3.25 molar solution. So to solve that, I would end up with the liters equals 0.958 divided by 3.25, and that would leave me with 0.295 liters, which would be 295 milliliters. How many liters of 0.05 molar salt solution can be made from 6.4 liters of 8 molar salt solution? So I have a concentrated solution of 8 molar salt water, and I've got a fair amount of it. I've got 6 liters, and I want to dilute it so that the concentration is only 0.05 molar. So I'm going to need to dilute it a lot. I'm going to need to add a lot of water. We end up with a big number here, and that's okay. The equation we're going to use here is called the dilution equation because we're diluting the solution. The starting molarity times the starting volume equals the final molarity times the final volume. We're given a starting molarity of 8. We're given a starting volume of 6.4 liters. And then we want our final molarity to be 0.05. And we want to know how many liters that would take. So we divide both sides by 0.05. 0.05 cancels out on this side. 8 times 6.4 divided by 0.05 ends up with 1,024 liters that we would need to dilute it to. Okay, calculate the molality of a solution containing 100 grams of potassium chloride in 150 grams of water. Molality equals moles of solute per kilograms of solvent. So we're given the kilograms of solvent, we're given the grams of solvent, which is 150. 150 grams is 0.150 kilograms. Move the decimal point 1, 2, 3 places to the left. So I need the moles of solute. Again, I'm not given the moles, but moles equals grams times molar mass. So 100 divided by the molar mass of potassium chloride, which is 74.4. Right, it's a potassium plus a chloride. So 100 divided by 74.4 is 1.34 moles. That's the number I'm going to put back over here, 1.34 moles divided by 0.15 kilograms gives us a molality of 8.93 molal. What temperature will the solution from, should have just said the previous problem, which was number 13, boil at? Okay, the calculation for the change in boiling point is the I times the boiling point constant times the concentration or molality. Okay, so in the last problem we had 8.93 molal solution of KCl. So we've got the concentration, 8.93. We've got the Kb. We need to know the I, which is called the Van Hoff factor. Well, this is an ionic compound. It's a metal and a nonmetal. It's got a chloride. Again, that's a big clue that this is going to break apart. So the I is going to be greater than 1. And in this case, it's going to be 2 because it's going to break into one potassium and 1 chlorine. So 2 times the boiling point constant of 0.512 times the concentration of 8.93 gives us a change in boiling temperature of 9.14 degrees Celsius. That's not the answer, though. The answer is, what is the new boiling point? Well, the original boiling point of water is 100 degrees Celsius, and we have calculated that the change in the boiling point is going to be 9.14, which means the new boiling point is 109.14 degrees Celsius. With boiling points, you add the difference that you find with the formula. In the freezing points, you subtract. Okay, determine the molar mass of a compound that forms 8.4 liters of a 2.1 molar solution when 200 grams of the substance have been dissolved. All right, so molarity equals moles per liter. We're given the molarity, it's 2.1 molar. We're given the liters, it's 8.4 liters. We're not given the moles. But we can find the moles. We multiply 8.4 times 2.1, and we find that the number of moles is 17.64 moles. Well, 17.64 moles we have we were given 200 grams. So if the number of moles equals the grams divided by the molar mass, then that means that the molar mass is equal to the grams divided by the number of moles. Now we can find the molar mass. So the molar mass is molar mass is 200 grams divided by 17.64 moles. And when you do that out, you find that the molar mass is 11.34 grams. Okay, so we've conducted an imaginary or hypothetical lab here. So we are dissolving, or we are putting in magnesium chloride in water. First question, what is the solute? What is the solvent? Well, remember, the solute is the thing that gets dissolved. The solvent is the thing that is dissolved into, or that does the dissolving. So the solute, the thing that's being dissolved, is the magnesium chloride. The thing that does the dissolving, or the solvent, is the water, H2O. What is the mass of the magnesium chloride used in the experiment? Well, if we go back to the table here, it says that the empty beaker weighed 142.4, and the beaker with the salt in it, the magnesium chloride in it, after all the water had been boiled away, was 172.6. So the mass of the magnesium is the difference, 172.6. That's the mass of the dry beaker with the salt in it, minus the mass of the empty beaker, which was 142.4, means that the salt had a mass of 30.2 grams. The mass of the water? Well, the mass of the water is the difference between the mass of the solution. Okay, the solution had a mass of 176, and then after the water was driven away or boiled off, what was left was the glass, the beaker, the salt, minus the water. So we take the total of the whole solution in the beaker and subtract the beaker and the dried salt, and that would be 216.3 minus 172.6, and that gives us a mass of water of 43.7 grams. Now we need to do mole calculations. All right, moles is the number of grams divided by the molar mass. So for the magnesium chloride, we said we had 30.2 grams. The mass of magnesium chloride, that's 95.1 grams. So we divide those together and we find that there was 0.318 moles of magnesium chloride. And then we do this for water. We have 43.7 grams of water. Water has a mass of 18 grams. 43 divided by 18 is 2.43 moles of water. Okay, so we know how many grams of each substance, how many moles of each substance. So we can do some calculations here. Molarity is moles per liter. Well, the moles of the magnesium chloride is 0.312. The number of liters is 75.2. That's in the table back at the beginning, which is 75.2 milliliters, which means 0.0752 liters, which means that the solution had a concentration of 4.23 molar. The molality of the solution is moles per kilogram of solvent, Well, it's 0.312 moles of magnesium chloride, and the solvent was 43.7 grams, which means 0.0437 kilograms. When we divide that, we get a molality of 7.28 molal. And then the last question is, what is the solubility of magnesium per 100 grams of H2O? This one we're going to do as a proportion according to our first couple of calculations. We said that there were 30.2 grams of magnesium chloride dissolved in 43.7 grams of H2O. So the question then is, how many grams of magnesium chloride would be dissolved if we had 100 grams of H2O? So we cross multiply here, 30.2 times 100 divided by 43.7. And we would find that you could have 69.1 grams per 100 grams of H2O. Okay, what are the theoretical boiling and freezing points of this solution? So, again, we've got the delta TB, how much the boiling point is going to change, is I times KB times molality. Well, we've got magnesium chloride. There's those chlorides. Okay, that's the clue. There's two chlorides, there's one magnesium, which means I has a value of 3. It's going to break into 3 different pieces, 1 magnesium and 2 chlorides. KB is given to you right here, 0.512. The molality, well, we calculated that back here at 7.28. So we're going to drop that into our formula here. When we do that math, we get a result of 11.18 degrees Celsius. That's how much the boiling point is going to change. That's what the delta TB means, change in boiling temperature. Since we're talking about water, it started out at 100, we add 11.18. That means the new theoretical boiling point of this solution would be 111.18 degrees Celsius. The freezing point, we're going to do essentially the same thing. Calculation, the formula is the same except that it's a different constant. Sorry, that's delta TF. Delta TF equals 3 times, this time it's 1.86 for freezing of water. Concentration is the same, 7.28. Do that math, we get a result of 40.62. And then since the normal freezing point of water is 0, we subtract, because the boiling point goes up, the freezing point goes down. We subtract 40.62. So the new boiling point would be negative 40.62 degrees Celsius. Okay, so there you have it. You need to be able to calculate molarity, molality, percent by mass, possibly the boiling and freezing point formulas, which we have here. You need to understand the effect of things like ionic compounds versus non-electrolytes on solutions, the solubility, be able to read the solubility chart like we had at the beginning, and do some small calculations with that. And then understand the basic principles of what are called the colligative properties, which is that adding solute to a solvent increases its boiling point, lowers its freezing point. There you have it.